the Vesper model is looking at the different geometries that we've talked about in lab last week, and how you can use the types of bonds and the electron pairs to determine what the shapes of these molecules will be in 3 dimensions. And that the whole goal behind this is that you want to have the bonding pairs of electrons be spread apart as far as possible, as well as the lone electron pairs, because they repel each other and they have little to no interest in being held closely together. If you have lone pairs versus bonding pairs, lone pairs will always win. Lone pairs are going to be able to exert more of a force. They are a slightly bigger bully. So these are the base structures depending on how many atoms we have connected. If you just have 2 atoms, it would be a straight line, which also would be linear. But typically when you have 2 atoms off of your center atom, you'll have a linear shape. When you have 3 atoms off of your center atom, you'll have a 120-degree angle, and you will make a triangle that's in the same plane as each other. If you have 4 atoms connected to get to the central atom, you'll find a tetrahedral geometry that will have an angle of 109.5. With the trigonal bipyramidal, you will have both 90 and 120-degree angles, because the triangle in the middle that's serving as the base for your pyramid will act like trigonal planar, and they'll be 120 degrees apart, whereas the atoms that are forming the points on your pyramid will be 90 degrees away from each of the atoms that are in the triangle plane, the trigonal planar shape. And then finally, with octahedral, we will have 6 atoms connected to the center atom. Each of the 4 that's serving in the middle as a square planar will be 90 degrees apart from one another, and then the 2 on the outside will be 180. But if you are looking at each one, both on the top and bottom, the top part, well, the spokes will always be 90 degrees away from each other. And I seem to like skipping ahead today, I'm sorry. When you have 4 pairs of electrons, you will see that the bond angle between the atoms will become smaller and smaller as you increase the number of lone electron pairs. Again, that's because the lone electron pair distorts the geometry and pushes the bonding electron pairs slightly closer together. So we see with methane, everything's able to be distributed equally around the molecule, and so we'll see that angle be pretty consistent. With a trigonal pyramidal geometry like ammonia, where we have the single lone electron pair, the 3 atoms that are making the base of that pyramid are going to be pushed slightly closer together to allow extra space for that lone electron pair. And then we will see that that bond continues to shrink further when we reach something like water, where we have 2 lone electron pairs that are trying to get as far apart from each other as they can. And so the bonding electron pairs end up getting a little more close together than that you would have expected in the tetrahedral shape. We see similar things happen with both 5 and 6 electron pairs. When you have lost one of the bonds in the trigonal pyramidal geometry, you make a seesaw geometry. That 1 electron pair again tries to get as far away from everything else as it can. When you have 2 electron pairs, now you're pushing the angles even closer together, and you make a T-shaped geometry. And when you have 3, those are going to take over the trigonal part of the plane and causing the bonding electron pairs to get 180 degrees away from each other. We've already talked about octahedral. With square pyramidal, we will have that 1 lone electron pair separate from everything else. And then with square planar, we will see the electron pair taking over the 180 degree atoms, so that the 4 atoms that are in the square plane will stay put, and the 2 lone electron pairs will be completely opposite one another at 180 degree angles. So we're going to take a look at the shapes of H3O plus and ClF3 plus. I had you guys draw these shapes in. I'm not as concerned that you get caught up on the filled-in triangles, filled-in wedges versus the dashed wedges. The filled-in wedges just means that that bond is coming out at you, and the dashed wedge means it's coming from behind. And when you don't see a line per se or a wedge, that's just in the same plane together. With H3O+, we see we have 3 pairs of electrons that are being shared and 1 lone electron pair. So when we have that 3 shared pairs of electrons along with the lone electron pair, we know we're talking about something with 4 pairs. And then with the electron pair taking the place of one of the bonds, we know that that means it's going to be a pyramidal geometry. With ClF3+, we can see, having drawn the structure out, we have 2 pairs of shared electrons along that central atom, 2 bonded pairs, and from what we saw previously, when you have 2 of each, you will be a bent geometry. Sometimes that's called V-shape. Your textbook's also got listed here angular. First time I've heard of that one, but I guess that's a new name for it. So bent, angular, or V-shape, they are all synonymous with that distorted geometry. ICl4-, we see I in the center. It has 4 atoms that are connected to it and 2 pairs of lone electrons. So that's going to fall under our octahedral, but we're going to replace 2 of the bonds with lone pairs. And those are going to replace both the bonding pair at the top and the bottom, causing us to have a square planar geometry. The final part I think that we're reviewing, I may have thrown hybridization in there too, so bear with me, is dipoles, which is just a fancy way to say polar. When you have one side of the molecule that is holding on to electrons more than the other. Water here, we see oxygen with the 2 lone electron pairs. It's going to be slightly more negative than the positive hydrogens. It's going to pull the electron pair that's shared between the hydrogen and oxygen closer to it and pull it away from the hydrogen atoms. And this is what allows water to kind of act as a universal solvent. Because of that polar nature, it can dissolve almost all things that are also polar, as long as the intermolecular forces between the two are fairly similar. But we'll save that for another class. Here are some examples of both polar and nonpolar molecules. We see with BF3 that even though these bonds are polar, because we have boron, which is really positive in terms of wanting electrons compared to fluorine, that the bond is going to go more towards the fluorine side of the atoms in terms of the electrons being shared. When the arrow is pointing in that direction, it means you have more electrons. All of these, however, are sharing electrons the same way, which is why there is no net polar component to this molecule. This would be a nonpolar molecule because everything about it is being shared evenly. With this one here, we have Cl2CO. We have 2 chlorine atoms here at the bottom. We have the oxygen atom up top, and it's formed a double bond. This one has a couple of different things that I like to say are good hallmarks of, I skipped one, of polarity. We have a multiple bond between one of the atoms, but not with the others that are connected to the center atom. And we also have different types of atoms that are connected to the center atom. The other one that we tend to see are lone electron pairs. With this one, we have the electrons being pulled away from the center atom, but they are being pulled very differently. We've got the double bonded oxygen up here, the single bonded chlorines up here. So there is no way to have this molecule evenly distribute the electrons within it. And that double bond is actually going to push the electrons more towards the oxygen component of the molecule rather than the 2 fluorine atoms. So this would have a polar, be considered a polar molecule. With ammonia, nitrogen is our more electronegative atom, and so we see that the polarity is going towards that nitrogen atom. The hydrogens are going to be more positive, and so we see that all of the arrows are pointing towards nitrogen. So that one is going to be much more negative than the 3 hydrogen atoms, and so it too will be polar. I've got two examples here for you, SF4 and NF3. SF4 is going to have the 4 fluorine atoms that are going to be more electronegative than sulfur, pulling those electrons away. And with SF4, there are 34 valence electrons, 17 pairs. We will take care of 16 of them with the fluorine atoms, but there will also be a pair on this sulfur atom. And again, I told you there are 3 things I tend to look at, and lone electron pairs is a third. Anytime you have a single lone electron pair, the molecule will be polar because there is nothing in that molecule to cancel out that super strong electron pair that's pulling the electrons away from the rest of the bonds. Same thing occurs with NF3. There is a pair of electrons on the nitrogen atom. We see that although the fluorines this time are more polar than the nitrogen, they too are sharing electrons evenly between the 3 of them, but that lone electron pair sitting on top of nitrogen will push those bonds in closer together and cause this molecule to become more polar. The only way you can really tell from these structures would be to physically draw that Lewis structure and to look at where those electron pairs are landing. Alright, and from having skipped ahead inadvertently, there is one more part to this one, and that's hybridization.